Alright, let's pick back up where we left off. Suppose an object is moving along a horizontal line and the position of the object in meters is given by the position function 3t to the fourth minus 44t cubed plus 108t squared plus 20, where positions to the right of s equals 0 are considered positive. Find any values for t when the object is not moving, and when is the object moving to the left. Now, at first glance, this problem might look like something completely different than everything we've learned so far. But really, it's a problem that we've seen already in disguise. Find any values for t when the object is not moving. We were given a position function, so its derivative is the velocity. When an object is not moving, that means the velocity is 0. When is the object moving to the left? If we're taking the right to be the positive direction, then when it's moving to the left, that means the velocity is negative. This is the same problem, effectively, as the one we saw at the end of the first video for this topic. It's just written a little differently. It's in a context. It's in the position context rather than is the function increasing or decreasing. That's all. Let's calculate the derivative. So v of t is s prime of t would be 12t cubed minus 44 times 3 is 120, 132 t squared plus 108 times 2 is 216 t plus 20. Wait. The derivative of 20 is 0. So there's a plus 0 here, which I'm not going to write. We want to solve the velocity equal to 0. So let's solve 12t cubed minus 132t squared plus 216t equals 0. Let's see. I know I can factor out a 12 from 132. It's 12 times 11. Yeah. 216. Is 216 divisible by 12? I think so. It is. So I can factor out a 12t by t squared minus 11t plus 18. Now this trinomial here, the t squared minus 11t plus 18, that's relatively easy to factor. That's 12t by t minus 3, t minus 2 by t minus 9. So that tells me that there's 3 roots to the equation. T equals 0, 2, 9. So the object is not moving when t equals 0, 2, or 9. Now, when is the object moving to the left? Again, we want the velocity to be negative. We have the velocity function, and in fact, we have a factored form. Let's test on our number line. Here's our number line. Here's 0, here's 2, and here's 9. When is it moving to the left? We want the velocity to be negative. So let's test. But I'm going to test into the form 12t by t minus 2 by t minus 9, which is a form of the velocity function, right? It's just the factored form. So let's test, how about negative 1? If I test negative 1, let t equal negative 1. Then 12t would be negative. T minus 2, negative 1 minus 2 would be negative. Negative 1 minus 9 would be negative. Negative times a negative, so v of negative 1 would be negative. Let's test positive 1. 12 times 1 would be positive. 1 minus 2 would be negative. 1 minus 9 would be negative, so that would be positive. So v of 1 would be positive. So this was negative. This was positive. All right, let's test, I don't know, how about 5? And I'm just picking random numbers in each interval. 12 times 5 would be positive. 5 minus 2 would be positive. 5 minus 9 would be negative. Positive times a negative would be negative. V of 5 would be negative. And how about a number greater than 9? How about 10? Let's test t equal 10. So then that would be positive times a positive times a positive, which would be positive. V of 10 would be positive. When is the object moving to the left? If it's moving to the left, then its velocity is negative. So, it's moving to the left. When t is in the intervals negative infinity to 0 and 2 to 9. Alright, so we've seen how we can use that same concept of finding the zeros and testing in intervals in a couple different situations. That's actually going to be really important as we progress through this course. Let's build a few more differentiation formulas. Alright, and we actually sort of saw this example, the derivative with respect to x of the sine function. We saw this graphically in the previous topic, but let's actually prove it. So the derivative with respect to x of the sine function, all right, well, that would be the limit with h approaching 0 of the sine of x plus h minus the sine of x over h. I can't substitute 0 right now. It would be indeterminate, so I have to evaluate the sine of x plus h. And we can't just distribute the sine. It just doesn't work. But what we can do is remember that there's that sum formula for the sine function, which hopefully you saw, I'm definitely sure you saw back in trigonometry. And whether you remember it or not, I can't answer that right now. But we'd have the limit with h approaching 0. The sine of x plus h is sine x cosine h minus cosine x, plus cosine x sine h minus sine x all over h. Alright, so that's the sum. I use the sum identity for the sine function. Now what I'm going to do is I'm going to rearrange this and regroup things a little bit. So what I'm going to do is I'm going to put the two terms that have the sine x cosine a, the sine x together, I'm going to factor that out. So then this becomes the limit with h approaching 0. And I have sine x times cosine h minus 1 over h. And then I have this other term plus cosine x times sine h over h. And I'm going to break this up into two separate limits. This is the limit with h approaching 0. Well, actually, notice I can, let's actually change this up a little bit. Notice that this sine x does not depend on h. I can sort of bring it outside. Similarly, that cosine x does not depend on h. I can bring it outside. So I can rewrite this as sine x times the limit with h approaching 0 of cosine of h minus 1 over h plus cosine x times the limit with h approaching 0 of sine of h over h. Now, we learned about these special limits back in the limits topic in Unit 1, and these are special limits. The limit with h approaching 0 of cosine h minus 1 over h, that's a special limit. The limit with h approaching 0 of sine h over h is a special limit. It turns out, if you remember, that this first limit with h approaching 0 of cosine h minus 1 over h, this limit goes to 0. And then the limit with h approaching 0 of sine h over h, that limit goes to 1. So we end up with, through some arithmetic here, I have sine x times 0 plus cosine x times 1. The derivative with respect to x of the sine function of sine x is cosine x. And we can do something similar with the derivative with respect to x of the cosine function. This is then equal to the limit with h approaching 0 of cosine of x plus h minus cosine of x over h. We expand using the cosine identity. That's cosine x cosine h minus sine x sine h minus cosine x over h. And then we do a similar thing. We break this, we regroup. This is the limit with h approaching 0. And again, I'm going to group together the terms that have the cosine x in them. So that's the limit with h approaching 0. I'd have cosine x times cosine h minus 1 over h plus, minus sine x times sine h over h. And again, we break this up using the same pattern. This is then cosine x, right, because not dependent on h, times the limit with h approaching 0. And notice we see that same limit, cosine h minus 1 over h minus sine x times the limit with h approaching 0 of sine h over h. And again, notice the same exact thing happens here. That the first limit, the limit with the cosines, goes to 0. The limit with the sines, right, this limit, that goes to 0. The second limit goes to 1. And so we are left with the derivative with respect to x of the cosine function is equal to negative sine x. So that's how we can calculate the derivative of the sine function and the cosine function respectively. The derivative of the sine is the cosine. The derivative of the cosine is negative sine. A couple other formulas. What's the derivative with respect to x of the basic exponential, the base e exponential e to the x? Well, if we apply the limit h approaching 0, I'd have e to the x plus h minus e to the x over h. I can break up that e to the x plus h. That's e to the x times e to the h. Remember your rules for exponents. Minus e to the x over h. I can factor out the e to the x and bring it outside, sort of using a similar trick that we saw in the previous slide. So then that's e to the x times the limit with h approaching 0 of e to the h minus 1 over h. Now this limit is an indeterminate form, and I cannot prove it to you right now that this limit is exactly 1. This limit is 1. Okay? Can't prove it right now. I don't have the techniques available. You can verify it numerically. If you try this out on a calculator, the limit with h approaching 0 of e to the h minus 1 over h, and build a table like we did in the limit topics, you will see that this limit is 1. And so it turns out that the derivative with respect to x of e to the x is e to the x. It's a very nice rule. This function is its own derivative. That's pretty neat. Now, this next one, the derivative of the natural log function, I cannot prove to you right now. I don't have the tools available. We're going to prove it in a later topic, but we will accept that the derivative with respect to x of the natural log of x is 1 over x, and we'll prove this later. We'll see this later on in this unit, but we have to talk about inverse functions and how the derivatives of inverse functions work. Then we can prove this one. All right, so find the derivative of each function. Let me go back, as I didn't mention this. The derivative with respect to x of e to the x is e to the x. Now, if we wanted the derivative with respect to x of a to the x, then it follows a slightly similar pattern. This ends up being, and I won't prove this right now, this ends up being a to the x times the natural log of a. Similarly, the derivative with respect to x of the logarithm base a of x is 1 over x times the natural log of a. And for both of these, where a is a constant, right? Where a is a constant and really should be positive. Okay? All right, so now let's go back to this one. Let's find some derivatives again. Let's find the derivative of the function g of t is 3 to the t minus 7 times the cosine of t. All right, well then g prime of t. The derivative of 3 to the t, using what we saw in the previous example, previous slide, that would be 3 to the t times the natural log of 3 minus 7. Then the derivative of the cosine function is negative sine t. So I would write g prime of t is 3 to the t times the natural log of 3 plus 7 sine t. R of p is 2 e to the p minus log 2 of p minus 8 sine p. Why don't you try this one on your own? Pause, see if you can find the derivative. All right, r prime of p would be 2 times, now p is my independent variable, my input, so the derivative of e to the p is e to the p, minus log base 2 of p, that would be 1 over p times the natural log of 2. 8 sine p, so minus 8 times cosine p. The derivative of the sine is cosine. And, we could get rid of the dots for multiplication, but basically that's what I would write. 2 e to the p minus 1 over p natural log 2 minus 8 cosine p is the derivative. All right, let's finish off this topic with one more application. Another motion problem. Here we are given that an object is moving along a horizontal line, and the position of the object in feet is given by the position function 2t minus 4 cosine t, where positions to the right are considered positive. And t is on the interval 0 to 2 pi, so we have a restricted domain here. Find the values for t, where the object is not moving. When is the object moving to the right? And then find the acceleration of the object after pi seconds. All right, so not moving. It's not moving. Actually, now would be a good time to pause. Try this one out on your own. See if you can do it. All right, not moving. That tells me that the velocity is 0. Moving to the right. I want the velocity to be positive. The acceleration after pi seconds. I'll calculate the acceleration function. We'll do that. Let's solve the first two first. All right, so the velocity function would be the derivative of the position function, which would be 2 minus 4 times negative sine t. So the velocity function is 2 plus 4 sine t. When is it not moving? So let's call this part A. When is it not moving? I need to solve 2 plus 4 sine t is 0. All right, so a little bit of algebra here. That means that sine t is negative 2 over 4, so sine t is negative 1/2. All right, I can answer that with my knowledge of the unit circle. If I'm thinking of 0 to 2 pi, where is the sine? Where is the b coordinate? Negative 1/2. T would be 7 pi over 6, and t would be 11 pi over 6. Those would be the two values of t on 0 to 2 pi that give us that those values. That give us the derivative equal to 0. So that's when it's not moving. Now, part B. Now that we know that, now let's figure out where is it moving to the right. We want the velocity, we want the derivative to be positive. So let's set up our number line. But now we only care about from 0 to 2 pi. So here's 0. 7 pi over 6 is a little bit more than pi, so here's 7 pi over 6. And here's 11 pi over 6. And then here's 2 pi. And we need to test into the derivative. Let's test into v of t is 2 plus 4 sine t. All right, and we can test any values that we want that are in those intervals. So let's see. Between 0 and 7 pi over 6, pi. V of pi, the velocity at pi, would be 2 plus 4 times the sine of pi. Well, the sine of pi is 0. So that's 2 plus 0, that's 2, which is positive. Testing between 7 pi over 6 and 11 pi over 6. How about 3 pi over 2? The velocity at 3 pi over 2. At 3 pi over 2, the sine is negative 1, so that would be 2 plus negative 4, which is negative 2, which is, of course, negative. And we can actually test at 2 pi, but even if we were to test between 11 pi over 6 and 2 pi, one in any of those values, it would end up being positive. But let's just go ahead and test 2 pi. The velocity at 2 pi would be, again, 2 plus 0, which is 2, which is positive. All right, so when is it moving to the right? That means the velocity is positive. So then moving to the right, that would be when t is on the intervals 0 to 7 pi over 6, and then 11 pi over 6 to 2 pi. All right, then finally part C. Find the acceleration of the object after pi seconds. The acceleration, all right, so the acceleration of the object is the derivative of the velocity, and the velocity is 2 plus 4 sine t, so that would be then 0 plus 4 times the cosine of t, so there's 4 cosine t. So then the acceleration at pi would be 4 times the cosine of pi. The cosine of pi is -1, so it would be 4 times -1. That would be -4. And then what would the units be? Well, the position is in feet, right? And the time is in seconds, right? We're told seconds. So the position is in feet, the velocity is in feet per second, the acceleration is in feet per second square. Feet per second per second. All right, so that concludes this second video for the topic. We've learned some basic rules for derivatives. But we're still sort of limited on what we can differentiate. In the upcoming sections, we're going to build on that knowledge and figure out how we can differentiate more complicated expressions, and of course see some examples of how to use them. All right, have a great day. See you next time.